All right, our first presenter unfortunately can't be here today in this stage, but obviously we have technology. This is Lee Salmon. He was just recently graduated, and he will be presenting from Philly today. But his topic today is going to be about the research he's done this summer with Mark and Andrew at the Cloud Lab called InfraAct. And to that extent, let me just, Lee, can you speak up a little? Lee, are you there? Lee, can you hear us? My speakers. Oh, these might be your call. Is it right?
I'm just wondering, yeah, if you're going to into these. But you can unplug it to see if you can hear on top of that.
Lee, can you speak up?
Oh,
okay.
that's okay.
Can you guys hear? Yeah, that's good. Go for it. Good.
Right, well, those are amazing products. So this summer, what you were talking about was the manner in which we started the process, where you begin with an idea of what you coding. events. And they would create this matrix, and then the question is, what can we as designers come up with a response to that? So here's just like a bunch that so they're on the website, and I'll continue to update this. But hopefully we can come up with new clever pairings based on multiple playing this game of numbers and continuing to produce more and more out. So here are some that I just came up with. You know, just connecting a few APIs and activities. I'm not going to go through all these, but they're on the site. And then I started to build this into a simple app that would hopefully be updated in real time. At the moment, it's still very basic, and it just has these 3 sliders and the existing combinations. So one of the questions right now, the outcomes depend very much on our own ability to make something. You know, the one thing I'd like to build into it is specific criteria that we can evaluate these on, perhaps on existing market shares or image-based reaction if we're drawn to how long we look at these, or if we are drawn to specific icons. Creating a forum for interest, so perhaps a way to constantly discuss these new possibilities. And I think it'd be interesting to also take some of these terms and to automatically begin to search the various app stores and see what exists. See if there are perhaps holes or opportunities where we can go in and approach this from a new point of view. So that's basically the project I was working on, and I'm going to continue to try to build on this script so it's more real time and building evaluation criteria into scripts. That's basically it. Okay.
Lee, can you take us through a few instances
Sure.
and decode them for us?
Yeah. Let's go to this site. So let's take a look at. Now, the thing about it is it gets quite absurd, which is more of the funny thing. But let's go. All right. So here on the upper left-hand corner we have activities, so simply ratings. Okay. We have an infrastructure that could be agricultural interests. The frameworks could be some sort of type of media player, and I give it general action, meaning perhaps as a prompt to inspire action. So for this component, there's all these criteria and sort of into it how it does hopefully spur some sort of idea. So for instance here, maybe it leads us down a conversation of trying to rate agricultural products based on some sort of reporting or interaction with that. I mean, maybe about community gardening and then blogs. I'm not really sure. So the idea is that something like this, though, just by pairing these simple icons and terms, it may prompt new ideas.
So can you reverse engineer, for instance, how the 3 sliders produce those results?
Sure. Just through the script, you mean?
Or just in any one of these examples?
Yeah, I mean, so I loaded in as many activities as I could think of, just the simple ones, activities and objects, right? And then all the data that's coming in from, say, these different APIs, they're coming from into Excel files, and they go into a path. But the idea is that each of these, they're all segmented into just tranches of what I'm putting in as scale, reach, and current, right? So the Google Trends, for instance, if I let's pull over here. If I pull up, so there's a certain way of building thresholds into it that if I want to be very current, it opens up all these boxes. But if I downplay, it basically starts to knock out certain priorities. And then in addition, I've segmented each Excel file into top rated and also top busy. So perhaps if you're not so concerned with
All right, thanks, Lee.
All right, thank you.
No, Charles, you guys want to? We are going to have to clear off. Oh, you want to put in? Or?
No, no.
So our application, which Noah and I developed during architecture under Torre and Block, is called Remote View. And the idea is that it was to create a synchronized sort of description or view of a place from multiple perspectives, effectively creating an instance. The way it started off was we were looking at a variety of applications that are currently available, which utilize a single camera or multiple cameras to stitch together a comprehensive point of view. Applications such as Photosynth, 3D panorama programs, panoramic cameras that do it all in one, and other photo stitches. So, rethinking this, what we were proposing with applications is to flip the scenario and capture many different perspectives in a single instance. Our intention was to harness the potential of mobile devices in particular, which are widely available and everybody has them. But there's this hidden potential which hasn't been exploited. As architecture students, we spend a lot of time analyzing space in various ways, but with now technology currently available to us, we're trying to use the power of these cameras, these portable devices, to reframe people's point of view. So what the app does is it instantaneously captures multiple perspectives of a given space from various cameras. So you can kind of think of it as having 1,000 lenses in one.
Yeah, so, I mean, it's a very simple concept, as I said, but yeah. So maybe the application of it, again, would start to apply in places where there's maybe a significant amount of people with a general interest in whatever the main subject is. So for instance, somewhere like a concert, which obviously, people now bring their phones and they'll hold those up as little lighting devices, or something maybe like a race. Any sort of general public place that would have a lot of people with a lot of potential accessible technology, right? And so then again, the power of this application would be that, as opposed to the other applications which currently exist, where, like Carson was saying, you can take a big panorama, or you can get a bigger idea of your surroundings from one point of view over the course of time, even if it's a few seconds. The power of the application that we're proposing is that you can get a bunch of different perspectives of maybe the same general subject at the same time. So essentially you can capture an instance of time from different points of view. So for instance, say you're standing here, then you could actually you could command all the cameras like, or all the devices that are currently running the application, to take a picture and you can record the instance of not only your perspective, but everyone else's perspective within the stadium or within the general area or within the event that you're currently attending. So to reiterate that, current devices, like you can see that even though you can capture a moment, like you can capture rather a series of moments, stitch them together over time, or proposing more. This is from the demo that we ran a while ago, is that we could capture the same moment of time, in this case Toro, right, from different perspectives. So for instance, someone was holding the camera in all different spots, that person was looking at the foot. But this is all taken at the exact same time, or more or less. We're working on that. But, yeah, controlled by a single user. Yeah, so we can show you, unfortunately our software crapped out a little bit, but we can more or less show you.
So what the software does is, if you guys have used iPhones or expert program applications, it goes kind of behind the framework, and instead of using the sort of AV framework to actually capture an image the standard way, what we're doing is we're actually capturing a live screenshot of whatever the cell phone is actually feeding out onto the screen. And what that allows is, it allows for an uninterrupted sort of view. And then it's just capturing a single screenshot.
Yeah, and so like you were saying, we have two different devices here, but each device has the potential to control the other device. And so if we had a bunch of devices, then theoretically, unfortunately we can't right now, but theoretically, one device could command all of the other devices to activate and to take a picture and then upload it.
Like Toro, are you running?
Yeah, I'm running it.
So effectively,
I'm going to take it.
yeah, I'll take a picture back of Toro. So Toro is going to control my phone.
It is.
Yes. Yeah, and then we refresh. We have it right now just uploading to a web page. And so you can see that top left image is the image of Carson's phone.
So I just took myself.
Yeah, you just
yeah, like I was saying, unfortunately our software kind of crapped out a little bit, but when we had it before, we could actually get like everyone in the room who was running the app to actually take a picture at the same time, which is quite interesting.
And the idea is, I mean, if one was to apply this to other applications such as Photosynth, it would put a different spin on basically the moment that's captured. It's one of an instance, which basically, if one thinks about it, it's a very different sort of perspective of a space than a stitched collective over several days. Anyway, yeah, so that's our application.
Okay, welcome everybody. I am presenting this kind of in lieu of a student who actually developed this in the context of our brain hacking studio last semester, a student named Anna Storage. She couldn't be here today. But basically we became very interested, especially in this studio, of actually reading the brain waves of architects as they're actually designing and trying to figure out what you can do in that context. Can you use this as a new mode of expression? Can you use this to learn what that person's thinking as they're working? But also, can we start to distribute this process of design over many people, right? So hundreds of thousands of people are wearing these brain waves. Can we start to expose them to architecture? architecture, or even learn how they're spatially processing that architecture by looking at their brain. So we became interested in a lot of these cases, especially that you find looking at the brain, where there's these quite fast pathways in the brain, where, for instance, I can show you an image, and literally within milliseconds, I can look at your visual cortex, which is in the backside of your brain, and I can read your brain waves just in that spot, and I can tell whether or not you've recognized something that I've asked you to look for. And what's really fascinating about this is that it actually happens much faster than you consciously realize you recognize something. So consciousness comes after, and this, again, these fast pathways in the brain are incredibly quick. They're in milliseconds. And so we're working with a neuroscientist who actually has developed this real-time computer vision software where he actually hacks into people's brains and trains them to look for things in images. And he can show them something like hundreds of images per second. So if you imagine images just flashing faster than you even think you can see. And he's actually pulling data out of your brain and using it as just a kind of generalized computation. So he's learning to use your brain as a computer. It's absolutely fascinating. He's building systems that hopefully we're going to start to deploy in architecture. Well, one of the interesting things we found during that process is he also used eye tracking. And when you start to look at the eye, you start to realize that the eye is also doing a lot of processing. And that this feeling that we have of evenness of vision, right? That we have this even field of vision, and that we're pretty much disinterested observers in this scene, and maybe we have a focal point and a periphery, but that's all. Turns out to be not true at all, right? It turns out that your eye is moving around constantly. So, you know, if anyone has ever looked at an eye up close, it's a pretty disgusting thing. If you haven't looked at your eye at the scale, you need to. I definitely recommend putting your eye right in front of your webcam and doing a record. And you look at the eye, and it's not only is it constantly moving, which is very typical. Play that one more time. But if you look at the pupil, right, the pupil's constantly dilating. This isn't just some response to lighting, right? But this is actually something that's driven by several factors, and that's giving us really important information about what that eye is processing. Now, normally we don't deal with that in architecture, right? Or normally we don't deal with that period in our daily lives, right? We accept the fact that our eye is darting around, and we're not really sure why. Now, there have been people that have really tried to rethink vision and really try to understand vision and the mechanics of vision. And one of the very important people to look at in this eye tracking technology is Alfred Yarbus, who's actually working, this pioneering work he did was actually in the 50s in the USSR, so it actually took a little bit to actually filter into the United States. Of course, this is during the Cold War. But he built these amazing contraptions, and you know, so you would actually place people into these things and observe how their eyes moved around. And again, you know, we're fascinated with this work of this neuroscientist because you know, not only do we know that neural recognition, this thing that he's working on, that again is faster than we think it is something that we can detect, but it's also something that we can actually give a subject a specific prompt to look for something in particular. Which means that we can really make a generalized tool from that knowledge. Well, it turns out the same is true for eyes. So when you put someone into these machines, and you start to show them imagery, and I apologize for the graininess of these photos, but if you can look in that corner there, it's a kind of scene of someone walking into a room, and there's a family, and they're looking at the person as they walk in. So this is typically how 7 different subjects without any prompt actually look at that image, right? And you see it's an incredibly diverse set, but at the same time there are these kind of typical densities that we find, right? And we would map these just to the heads, right? So as I'm looking out to you guys, I'm not seeing the architecture, I'm seeing your heads. My eyes implicitly moving around your heads, even though later my brain makes me think I'm seeing the architecture just as much. Right? But we see that there's, even though everybody does it differently, there's a kind of similarity to it too, which is fascinating. So we're all somewhat seen in the same way. What's even more incredible to me is that in each of these different images, Yarbus has given his subject a different prompt. So I think in one, the first one I think is just no prompt. The second one is asked to look at the clothes the subjects are wearing. One, which is the most interesting to me, is this last one, where he asked the subject to tell how long it had been since each person in that photo had seen the other people in the photo, right? So he asked for this very specific kind of social understanding of that scene. And if you look at where the eyes go, they go straight for the heads, right? Again, they're looking for almost the facial expressions of those people, right? It kind of shows that if you know where the eye's moving and you can start to ask really specific questions and you can detect that eye movement, then you can start to really build sophisticated tools that talk about how we process images, how we process space, what's important to us, what's the most salient aspects of space. So to us, it's very exciting. So this is why we went about building this very simple machine. So this is kind of fashion for geeks right here. So very simply, this is, you know, a glasses frame, right, that has had the lenses removed. We have a very simple webcam that's installed here. This is actually a PS3 webcam, and a lot of the technology that we play with in the Cloud Lab is actually game technology, because it turns out that's the cheapest and the best technology that's out there. And of course, this would normally be plugged into the computer. And I would give you guys a live demonstration, but unfortunately the light, we need a lot more light. For the next iteration, we're actually looking to mount a lot of infrared LEDs on this so that we can start to use this in more environments. So this is what we built. And again, this follows from the iWriter project, which is an open source project that's basically is out there and began as a way to give artists some more interesting tools, and especially to give people that have limited mobility or for instance, paralyzed people, the ability to have artistic expression again. So just by using their eyes, for instance, they can paint on a canvas. So we're using it in a slightly different way. Again, we're very interested in understanding the processing that's going on in our heads, in our eyes, that we don't even know about, right? But we think it's telling. We think it's going to tell us something about how people process buildings. So this is, you know, makes it look too technical, because if you look at my model here, you'll see that there's zip ties and there's, you know, masking tape and foam and things like that. But it kind of starts, of course, by thinking about how far away the camera is, and you know, it is a little bit of an exercise of hardware hacking, not too much, but some good old-fashioned glue. And you get to this point, and this is where you have your kind of incredible moment of seeing your own eyeball. So of course, we're doing this in software. We're using processing to basically take the webcam image. We're using OpenCV to actually figure out where that pupil is. It's amazing, like just for the simple glasses, that image of the eye is very consistent in terms of its placement in the field of view of the camera. So this is without too much error correction, without too much manipulation, we can get a very clear pupil. We can understand dilation, which is very useful to us too. And we can basically translate where that pupil is and create a projected location of the pupil on the screen. And that really is what the infrastructure of the entire thing. So once we can put that thing on a screen, we can figure out exactly where you're looking at. So we can present you things on the screen, and we can figure out where your eyes are going. Right, and so now maybe you have a little bit more information to think of this dot, right? So this is a person that's actively considering a computer screen, and the eyes are darting around, and we're just tracking that red dot. And I think our numbers there have to do with the area of the pupil. So this is the setup, right? Somebody wears this thing. This is Anna. This is the one who built this first one for our studio. And this is a bit of software that we've developed in processing, already starting to show the three-dimensional version. But of course, it's easier to start in 2D and consider two-dimensional images before we go to 3D. So again, what's fascinating to me about this is that we don't just show an image and start tracking the eye, but we give them a prompt. And I think the prompt is extremely important, because that really starts to bias the way that the eye moves. And I think it also gives our results some kind of more meaning, at least. So the context of this project was the Nakagin Tower in Tokyo. And so what we were doing is we were looking at these interiors and exteriors, And there's lots of examples of outdated technology, but also some of it's really interesting too. And we just ask very basic questions. So what would you keep? You know, this is a preservation project, but it's also something we want to intervene in. What do you keep and what do you get rid of? And what's fascinating to see is even from this very first experiment, it's somewhat crude, that you get these very different results, right? That, you know, in what we keep, it somewhat focuses more on the electronics, right? You see it darting around the edges. And what it wants to get rid of, almost kind of, it's almost the architect kind of finding these moments where they want to intervene, blankness, right? That's a blank canvas for us to kind of inject ourselves. So maybe this is more about how an architect processes space than a normal person. I think architects are all a little abnormal. So of course we have to start asking that question. Do architects see differently than just a regular person off the street? And what's the notion of expertise in even looking, right? Do we look differently? So, you know, so far somewhat inconclusive. Again, these haven't been really tested rigorously yet. But at least we have the start of kind of bringing people in and asking them to do this and comparing their results with results from architects. So again, this is two-dimensional work that we're looking at here, with just a very simple prompt. I think in this case it was, again, what would you keep? And we see these subjects, you know, seem to want to keep the Nakagin Tower. So again, whenever we find, you know, the density of points, we're kind of happy because we think we're onto something. But of course, we're architects, we're interested in environments, we're interested in the volumetric condition. So this produces sort of challenges in terms of how we display the geometry, how we visualize the results. It becomes a bit more difficult. In that project, we did start to take on this problem of 3D visualization. Heat mapping is a kind of conventional technique that's used in visualization, right? So we have more heat where they look longer, we have less heat where they don't look, right? And in this case, if they don't look at all, we just don't put any color. So you start to get an idea of even the way the eye darts around in even these very primitive settings, right? So the eye's movement is very particular. So these are these saccades of moving left and right consistently. And we know the mechanism of vision actually depends on the eye movement. If you actually hold your eyeball still, you won't actually be able to see anything. It needs to move around. And it's actually something about the optical flow that even allows you to discern your environment. Right, so we're looking at different base conditions here, not prompting very much, but just getting kind of the geometry figured out. And quickly we start to move into, again, a kind of three-dimensional representation of this building and a kind of painting, a kind of three-dimensional painting of the eye onto that piece of architecture. And so for us, again, this could just be a means of analysis, right? So I present to you a building that's already built. Where does your eye go? Can I prompt you in different ways? Can I ask you in the same way that Yarbus asked very particular social questions or gave very specific prompts? Can I also do this in this setting? In this case, the prompt was, again, what do you keep? And what's interesting about what we're seeing here, and I'll play it again, moves out, is that what we're not seeing is 6 different models or 5 different models. We're seeing the same model iterated many times. So in this case, Anna would ask, what do you keep? Wherever she got the brightest coloration, she would keep that part. Wherever her eye didn't go, she would delete. And so we see this almost deterioration of this model in different successions, right? So it starts to get a little bit more gnarly and eaten away at, so by the end it's quite deteriorated. And this was paired with also another study she did of where to intervene and adding new additional services. So I think it's very important that we don't just analyze, but we build, right? And we make new things. Okay, I can show you guys a slightly nicer rendering of that too. And again, all of our technology is somewhat borrowed from games. Not only the webcams and the hardware technology, but the software technology too. So these shading algorithms and baked in texture maps and things like that to get as real as possible, are all borrowed from games technology and all borrowed from techniques from real-time graphics and gaming. So for me, this is kind of a cheat. You actually wouldn't want to show someone what their eye was doing while the test is being run. You kind of compromise the results, but just in kind of visualizing what's happening, it's fascinating to see. So again, you see that study here, this heat mapping study of this three-dimensional building. And again, always used to actually manipulate the geometry, right? So we're not doing analysis, but we're asking how an analysis tool, or how a new form of sight, or at least a different kind of knowledge about how we see can actually inform how we make things. And I think that's a very important step. Okay, fair enough.
How are we ready?
Not yet.
All right. This is a kind of conversation continue of what Mark just described on the brain hacking studio. But this was, before we initiated that studio, we had this seminar in collaboration with Bobby Johnson and Daniel Nicky. They were students of ours who started the project by really investigating what is this brainwave that's coming out of the head. That kind of initiated this idea of New York City newer cartography. And we all know cartography is this kind of measurement of science, science of measurement. We, as architects, already know all about this because that's what we do every day, right? We draw these drawings, we have measurement, we have thickness, which we all know is called the kind of measurement of extensive. Now, the science or the kind of technology in architecture has shifted somewhat. It's always been talked about. It's nothing new, but it's the software that kind of visualizes these components to us much more vividly now, and these are the intensive properties of measurements, right? So structural, we know the stress inside of the material, which is not anything related to distance, is more related to the kind of density and air flows, temperature, all this measurement of intensity, or intensive measurement. Now, that kind of idea of measurement is nothing new. Architects are familiar with it. That's the kind of almost the foundation of science, that we measure things. Now, the things we've lately been getting into is this kind of human feedback measurement. And what Mark just showed us was one of the examples of the eyeball, eye tracking of architecture. And he spoke earlier about the neurofeedback the brain gives. So this is somewhat of a data that comes out of the brain, and as you can see, it's very noisy, it's almost hard to comprehend, but it is that measurement that we're going after. Now, Mark kind of briefly went over the group we were collaborating with at the biomedical engineer, Paul Saida. They use these very intensive caps that have 64 sensors or electrodes, which cover the scalp and kind of takes a global reading. And this is the example he was talking about, where you can show a subject many images, and you would be synchronizing the data of what was shown and the response after that, what the signals was like. Now, we kind of take that idea back to architecture and trying to combine all these measurements of how should they be, or what can be seen once we're synchronizing these data. So obviously, again, the extensive measurement of GPS or heading is the extensive of where are we in space, right? The XYZs that the GPX code, obviously you guys have been talking about. But then we take the brainwave data we call EEG. We know there's a certain frequency that's coming out, and that's a certain data we collect. And obviously not the extensive nature of our position and heading, but we also want to be able to represent the geometry we have. So here I call it building information management, but in simple, it's just geometry. So what is the sensor. In our case, we went the expensive route of iPhone and had to get the X code and have the program, etc. But obviously, it's the same device. You can collect your XYZ coordinate, or in this case, latitude, longitude. And obviously, the iPhone allows us to collect heading data. So where are you looking at? So this is the simple screenshot of the app. It's nothing fancy. We're not trying to visualize anything. This is just the kind of medium of collection of the data. Now, this is Bobby right here. So what you see is the headset. That's the actual EEG headset that collects your brainwave data. He has in his hand the iPhone that collects the GPS data, but also the heading data, and also has a Bluetooth connection with the headset, so also simultaneously collecting the EEG data. So what you do have is this collective synchronized data set, right? That's all that really is important, is that there is a timestamp, there's a location, there's a heading, and there's a certain frequency of data that's associated. So that's when I say combining all this measurement. If they're desynchronized, it doesn't really have value, but by having that synchronous timestamp, it starts to give us data that we can start looking at. So the site we chose is Lincoln Center, and you guys probably visited, or you will visit. The new lawn by Diller-Scofidio is this hyperbolic shape. The reason why we chose this site is not so much for the architecture, unfortunately, but more so to do with having to collect GPS data. So we need to be outside, we need to have good sky view. So unfortunately, there's not a technology that can give you your GPS location inside of the building yet. But obviously, it was an interesting site to walk around, having these elevations, kind of greenery, water, modern architecture, skyscrapers around. So this is somewhat off track of the presentation, but just to kind of speak of thinking about how we process these information is somewhat of a research topic that is ongoing. And as Mark said with his last video, it showed how the building was highlighted as the person was viewing already disturbs the actual input, right? Because the environment is changing and you react to the environment. So this idea that information being fed back actually is a plus, and it actually provides a different kind of response to the user or the experienced person. So given the fact that we have a location, so just imagine this camera as the camera head or the person's head. The head has the XYZ space. Obviously, we're just using latitude, longitude to locate the position. We have a generic kind of height, like how tall someone is and where it's directed. Now, what you see on the kind of wall canvas is the actual neural data. So we're spraying the actual measurement of the brainwave. So if you have a frequency of 0 to 60, and they're banded by 10, frequency of 10, so 0 to 10, 10 to 20, 20 to 10, so forth. Scientists have acknowledged a certain ratio in that frequency to identify a certain metric called attention and meditation values. So those are a little more advanced in the sense that they're computed values. So they took the whole band and they would identify what is attention, or if someone has more attention or not, or has more meditative values or not. So what you see in the speckled color is red is more attentive value, and cyan is more meditative value. So just a simple example is when you go to a beach, or you can just imagine a beach, you are actually emitting more alpha waves. So that alone scientifically is proven that there's a kind of calm state of mind that has a certain brain pattern that we can acknowledge now. So given the fact that we have this data, this is a visualization where the dotted line is the pathway in which we walked, and the spray is based on the actual circulation. So let me just pop you through these real quick and show you the actual video. So first off, I can show you quickly what the kind of neural data can look like over time. And this was an experiment Mark's done of simply again, what he calls prompt. What is the input? Eating pizza, Subway downtown, cigars and coffee. Very
cigarettes and
interesting inputs he's chosen. And so here's the actual, so you see it in animation, right? Because it's a timestamp over time, walking through the park or the space, and actually spraying your brains to the architecture. So, again, when it comes to proof of concept, this is probably as far as we get. In terms of analysis, we can obviously start to see areas that have higher cyan or lower cyan, higher magenta, lower magenta, which you could come to the conclusion that those state of space is providing that certain feedback, or let's say a certain qualitative amount of space. So again, in this context of architecture and technology, the probably the important thing was for us is that we try to bring back these different kind of measurements that's kind of ongoing and currently being available, is to bring it into the context of architectural space and to kind of figure out the usage of it. So as Mark says, it somewhat is an analytical tool at this stage, but it's not hard to imagine that these could be another feedback in order to Lee's the first presentation of if we could gather a lot of people's kind of input data from the brainwave based on this certain experience, that could be a certain kind of feedback. All right, that's it for me. Pablo, you ready?
Yeah, can I clarify that?
Sure. You want to plug?
Yeah. My name is Pablo Ross. I'm a current researcher at Columbia. I'm in this program called Advanced Architectural Research. And I'm studying how by fabrication, I'm researching doing fabrication and doing, instead of historical research that is also included in my study, I'm trying to learn things with this system, which is fabricating and creating objects. So my topic is neuroergonomy in architecture. I've discovered that the experience of our body is the one that provides the primary metaphors through which we organize our perception of the world. And for these, the senses are limiters of this knowledge of reality. So what I'm doing is using the new technologies to try to provide to the body new experiences and to try to make a progress in the relation between the body and the architect. So at the very first time we had this relation, this anthropomorphic relation in the Vitruvian man, which basically we were identifying buildings with the shapes of the bodies. With functionalism, we improved this, and we saw how the body could be a machine in the environment of the body, and we started controlling all the measurements and the dimensions of the building, and we were making relations between the bodies inside the building and controlling these relations. El modular tried to, I'm explaining really fast. In this mass production, it tried to restore the harmony between the humans and the environment through the use of the human scale in the mass production. So we had these furnitures that were adapting to our shapes, these buildings that were adapting to our body. But then the technology, the use of the computers changed again everything, and we started, instead of using the computers as a way to communicate the body with the buildings, we use the computer to make topological relations between the shapes of our designs and how these shapes were going to be developed. For me, the question is how to use these computers to again, have an application where the perception of our body could be read by the building. How the changes of the human neural system can affect in the shapes, in the transparency, in the what I say neural systems of the building. So there is this amazing this amazing use of techno-human interfaces that are providing us biofeedback, and that basically we can track, as Mark showed you, how we are thinking, how we are moving, how we are seeing, looking at the things, at our environment. So these technologies are already in the market. They exist mostly for medical purposes, sometimes military purposes, video gaming. But I think really interested if we can start thinking that these technologies could be also part of the architecture. I don't know why we cannot see this very well, but there are some examples, mostly artistic examples, where we discovered these realities, these new realities with the environments using these gadgets, these interfaces. Mostly they are focused in one of the senses, or in one of the parts of our body. Again, what if we could use this as in an architectural environment? That's the topic of my research. I'm trying to put together all these senses, enable this transmission to the building, and have a communication with the building. So that's the idea. The idea is connect our neural system to a chip. We became a kind of cyborgs. Plug the neural system to the computer. Then upload this information, so we can share this information. The building can receive this information, or the humans, we can receive also this information. And then control the environment with for instance, the movements of the body. So by doing this, being detected by a technology like electromuscle sensors, and programming this in the computers, we can transform the environment. It's a kind of voluntary process, but it can also be much more hidden process that we cannot entirely control. The thing is that we can use our senses as an input for the building, but we can receive also information. The idea is receiving also information from the building. So these sensors can provide also information, be an output. I'm speaking about putting electricity in, using the electricity of our body, augmenting it and converting it into digital data. But also the contrary, converting digital data into electricity and informing the building, informing the body to have this communication between the built environment and the humans. So we have this communication between the environment is built with the communication between the body and the systems of the building. Instead of the built environment is designed within, inside, not outside. And for this, I was using a really cheap, fast, portable systems, working with an Arduino board, controlling the reception of all these stimuli of the muscles. We designed this AMG board that converted the impulses into data, and we were finally connecting to the body. So, for instance, we could detect the respiration, we could measure the relaxation because we have a heartbeat. We can control the motor movement and so on. So I was mapping a little bit the body to find these reactions that we have in normal conditions, and build the whole neuromedallion. I'm calling it neuromedallion with very simple chip and technology. So I had this it's only 2 months since I started. I have very simple examples that show how my movements can be read by the computer. I mean, when I turn on the right, this information goes to this side of the screen. When I move on the left, it goes to the other side. So still I need to apply it into real cases, but I'm interested in maybe having this kind of, as it happened with the control of the airplanes, to have this kind of let's say, vocabulary of science that could mean things for the people. Or another one, just a very simple example of the rotation of the hand. Control the transparency or the opacity of the environment. So applying these movements to, an hypothesis of light, we could control the building. I think that these are very simple examples, but they help us to understand the potentiality of this neuromedallion. And finally, if we are able to communicate to the building and transform the building, it doesn't mean that we can communicate our bodies through another object that is the built environment. That's a good question for this research. I will try to think more about the applications and also these other questions. And using the neuromedallion for raising questions and add more information to the results. That's it.
Yeah, let's turn on the lights.